Hey everyone, welcome to this video on debugging nested arrow array types in memory. So this is a follow-up to my first video where I showed you how to debug integer types and string types in memory. I was surprised at how many people were interested and gave good feedback on that, so I decided to continue along and take a look at nested data types in Arrow. So when I'm talking about nested, I'm really talking about something that builds on top of another type. We're going to look at lists and structs in this video. They're not the only types, but they're pretty common. But you can really think of nested as like, especially I think with a list is the easiest to think about. Uh, it really just sits on top of another array and tells you like which ranges make a list element for you. Okay, so if that doesn't make sense, it's good that we're going to jump into this video and take a look at it in more detail. So I've expanded on the code that we worked with in the last video. I have two new functions, build list array and build struct array. Again, these don't really do anything. They just kind of build an array, release it, and be done with it. So not a super interesting program, but it's great to debug these different array types in memory. Okay, so I'm going to go ahead and set breakpoints on those two functions. I'll do break build list array, and I'll go ahead and set my break on build struct array a while. Just going to go ahead and run this program. And I'm stopped right here at build list array. So let's take a look at this code really quick to get a understanding of what we're doing with the nano arrow library to kind of build this at a very low level form. So when you're building a list type in Nano Arrow, you usually start with a schema and you say, I have a schema that's going to be a list type. Okay, that's good. But then you need to set the child type of that schema. Okay, so we see this schema.children0, which I'm going to set to a 32-bit integer. So list types have one child element, and here I'm saying I have a list that's going to contain 32-bit integers. In Arrow, list types are homogeneous, right? They just have one data type that they kind of contain. Once I have that schema set, I build my array. And then when I actually get to appending, which is a little bit different than the last video we looked at, I don't really append to the array itself directly. I append to the child element. So here, my first child element is an integer array. I say go ahead and append an integer to that. And I do the values 1, 2, 3. And yeah, then I just finish the element off. And that really means like my first list element is the numbers 1, 2, 3 all wrapped in one list. Okay. Then I'm going to append null, and then I make another list that contains the values 4 and 5 and finish that off, and I'm done building my array. So let's take a look at this by just going to the end of this function. And I have a length of 3, which I was kind of saying here. That's from the first element, appending null, and appending the third element. I have a null count of 1, 2 buffers, right, and 1 child, which we kind of talked about. So the first buffer is for most, if not every arrow array, it shows you the validity, excuse me, the validity bitmap. Okay, so if I look at array buffer 0, read from the least significant bit up. So I have 1, 0, 1, which means valid, invalid, valid. That's what I have here. Valid record, invalid when I append null, invalid record. So no surprises there. If I look at the second buffer, because I'm dealing with a list, which is a type that has 32-bit offsets, I'm going to use the word size. You could use large list if you wanted 64-bit offsets, but the default list type has 32-bit offsets. And even though our length is 3, I'm going to print 4 elements in decimal notation because the way lists work is you have length plus 1 values in the array buffers, first array buffer. So why do you have that? Well, it'll make more sense when we look at the child array, but really these are intervals. So they're right closed essentially, left open. So the first list element is comprised of elements starting at position 0 up to but not including 3. The second element, which was null, just kind of repeats the 3, has no length. That makes sense. And then the third element in my array, which we know here had 2 elements, starts at the 3rd offset and goes out to but not including the 5th offset of the child array. Okay, so it becomes helpful if you pair that by looking at the child array itself, which I'll go ahead and do here, print array children. We know that this is a 32-bit integer just because we constructed that way, as a length of 5, which is good. 1, 2, 3, 4, 5 is what I put into the code here, and 2 buffers. So in the last video, when we looked at integers, we saw that they had 2 buffers. So let's go ahead and take a look at that second buffer. And once again, we're dealing with 32-bit integers. I have a length of 5. So in this case, I'm going to print 5 words in decimal notation. And here we go, 1, 2, 3, 4, 5. That's exactly what I added here in my code. And again, when you match this up to the offsets from the top level array, 0 up to but not including the 3rd bound means my first list is really these 3 elements, which is what I had here. And then I have, once again, null. My 3rd array element starts at offset 3 and goes up to but not including 5. So that is 4 and 5, which is exactly what you see here. Okay, so just really want to drive home, this is why we consider a list like a nested type, because it kind of sits on top of another array type, in this case an integer, and just really provides offsets into that array itself, so you could see how you collect certain ranges into list elements in that higher level nested type. Okay, now let's jump down to the struct array, which is a little bit more complicated, but still fun to debug, not super crazy, I think, when you step through it this way. Let's look at the Nano Arrow code first. We're creating the schema with 2 children elements. Okay, so a struct can really be thought of, if you want to, as a data frame in a lot of cases. You have columns that you can kind of set here. So I'm creating a struct with 2 columns. The first is going to be a 32-bit integer named call1, and then the second is going to be a string type with the column 2 label there. I am creating that schema and start appending to my array. When it comes to the actual appends, you, just like in the list case, append to the children. So here I append to the first child element, the value 1, and I append to the second child element, the string foo, and then I finish that element. So think about, like, I don't know, even if you go through Excel or something, you go kind of row by row, column by column. I typed 1 into A1, foo into A2, and I hit enter, and I went down to the next line. It's kind of a crude way of thinking about it, but this arrow array finish element, again, is just going to make that element finish, or that row finish, however you want to think about it. I append null again, and then I repeat that same append to my first child, and int append to my second child a string, and finish that element to be done with it. And then I wrap up my entire array build out. So let's go ahead and go down to the place in the code where I know our array is finished, and I have a length of 3. Once again, just one buffer in this case, right? And that is the validity bitmap. So if I were to look at my first buffer, and we'll do this in binary again, same value as before, valid, invalid, valid, matches what I've done in code. Let's look at the first child element, and that, okay, kind of looks like that. I have a length of 3 and 2 buffers, and we'll look at the second one here. Once again, a length of 3 and 3 buffers this time. Okay. So it's kind of interesting. The difference in buffers is the string has a extra buffer to show you offsets. The primitive integer type does not need that. It's interesting that I really only appended 2 values, but I actually ended up with a length of 3. So Nano Arrow must be inserting, kind of a blank or dummy element into the children whenever null is appended. So not a problem at all there. Let's look at the values. So if I look at my children 0, and I'll look at my buffers 1, and I know this is a decimal word, and there's going to be 3 of them. Actually, I don't need 4. whoops, I don't need the pointer there either. And here we go, 1, 0, 2. So I never actually explicitly added 0, but when I added the null element, nano arrow must have gone down to each child and added a default value. Totally fine. It really doesn't matter. But in this case, yeah, I see 1, 0, 2. So the first struct element, and this row is 1, and then down to 2 for the third element. And then if I look at my other child, which I know is a string, let's take a look at that. Now remember, with strings, it's the second buffer, or third buffer actually, that has the string value itself, which is foobar, which combines all the string elements. And then if I were to look at the second buffer, that would give me the offsets that I need to access each element with +1, right? So if I'm starting for that first element and I want to know for my second buffer what that is, well, I'll start at 0, close at 3. 0, 1, 2 gets me the value of foo. 3 to 3 is a null type, and then 3 to 6 tells me, okay, start at the third element here up to, but not including 6. That gives me the word bar, and that is how the struct element is laid out. So again, they're called nested elements because they really sit on top of other array types and help you compose higher level abstractions. There's, of course, many more types than this. There's the map type, there's large lists, fixed length lists, even though they're less, I think, of a nested type than maybe these are. But yeah, there's quite a few. This is just two of the many that are in the Arrow specification. But what I hope you got out of this was just understanding how that parent-child relationship works, and just hone your skills in terms of debugging these Arrow arrays in memory. So good luck, and have fun programming.